might not need shoes to run, but damn it, they can help. Welcome back to another installment of the Applied Deep Learning course. Today, we're going to take a look at preprocessing, data augmentation, regularization, and a bit of visualization, and see how we can strap some shoes on our network so they run faster and better. But before we do that, let me quickly recap from last week's lecture. Last week we talked about transformer. So what is a transformer? A transformer basically is an encoder-decoder neural network that we can use for sequence processing in a similar way how we used recurrent neural networks, with one benefit, that a transformer does not have any recurrency in it. So we don't have this bottleneck in performance where we need sequential processing, but we can feed in the entire input sequence at once. The most essential building block that enables us to perform this operation is an attention mechanism that we have in our network. How this works is that the attention mechanism learns how individual words of our input relate to other words, or elements from our input relate to other elements, and can learn how to focus on how things relate to each other if you just take the entire sequence in one as once into your input. Why do we need positional encoding? So especially for natural language processing, we need to encode somehow the information where a word appears in our input. It could be at the beginning, it could be at the end, somewhere in the middle, and depending on where it appears, the word might mean something differently. The solution is to kind of also attach some sort of positional information to give the network the chance to also understand, wait, it's the same word, but it appeared somewhere differently, so it can make some sense out of this. What is the difference between the first attention block in the encoder and the first attention block in the decoder? Well, there are several differences, and I think the most important one is that the first attention block in the decoder is a so-called masked attention. And why is that a masked attention? Because it gets fed the output sequence, and it has to learn how words relate in our output sequence to each other. But if we feed in the entire output sequence and it should predict the output sequence, well, it doesn't make much sense, right? Because it would just learn to predict whatever next word it's reading in. So in order to solve this, we're masking out all the words that we haven't predicted yet, that are kind of from the future, and the network has to learn to predict them, and for the next step, we can then use those words. And if we feed in everything at once, we need to kind of mask out all values on the right top of our matrix to remove them from our input, so the network is forced to look at some other parts of the input for knowledge, and is not allowed to see any of the output of the target that it should predict in the future. How can transformers be used for object detection? I would say there are at least three things that can help in that regard, and that were also described in the paper, transformer detectors. And first of all, you need some sort of feature extraction. So instead of using word to vector, we basically use a standard convolutional neural network to extract features from our network. Then we feed it to an attention mechanism that learns how different parts of an image relate to each other. The second part is that for the decoder, we're having so-called object queries. And those object queries are being transformed. So one object query will be transformed in one output. And what those object queries are specific inputs, kind of learned guesses that say, okay, take a look at the left top and tell me if there is a kind of a small or a large object, something like that. You can think of it in that way, and those object queries are learned. So you have, say, 100 object queries, and then you have a maximum of 100 output predictions, and each object query learns where to look and for kind of what of shape of object they should look out for. And the third part is, once we have our output prediction, we need to define a loss and relate our output prediction with the ground truth set of boxes. And the mechanism they propose in that paper was bipartite matching loss, where you try to find the globally optimal assignment from the prediction to the output, to the ground truth. And you do this by comparing the boxes and the class labels and using the Hungarian algorithm to find the optimal assignment between those two sets in polynomial time. So that's the bipartite matching loss in a nutshell. And if you put all these together, you can actually perform object detection with transformers. Now to the shoes that help us running. Why do we need something like preprocessing? So there are a couple of reasons why preprocessing can be necessary or at least beneficial whenever you train a neural network. There are many parts of your network that assume normalized data. So input normalization is one major factor that you should definitely consider. For example, some default parameters like the learning rate assume that your data is normalized. Also, the parameter initialization strategies, Xavier initialization or He initialization, they also assume that your data is somehow normalized, so it can kind of make sense how to initialize all those weights in your network. And of course, every parameter update step is relying on this assumption, basically. So when you think about the gradient, what it does is we are computing the partial derivatives of all our parameters with respect to one single parameter to learn how to update that parameter. But the underlying assumption, therefore, is that we only change one parameter at a time and all other parameters stay the same, which is not what we're doing. What we're actually doing is we're updating all parameters at the same time. So when we're working on unnormalized data, this can degrade our performance significantly because the gradient can then easily explode or vanish as the distribution that we have going from one layer to the next layer kind of constantly changes. So if you have normalized data in your network layers, you can kind of overcome this problem. So the basic approach for doing this would be that you compute some statistics on your training set, and then you apply the very same operation on the training set, the validation set, and of course your test set. Input normalization, as I just said, is one of the most common and most important input operations that you should definitely have in your network. It's a very common preprocessing step, and it helps us to gain invariance to some undesired variations per sample. So if you have an image that is a bit brighter or a bit darker, that slight variation shouldn't affect whatever we're trying to achieve. So we can gain some invariance to these variations, intra-class variations, and ultimately it can support our training if we normalize our entire training set to make it look more homogeneous. The underlying assumption is the following, that certain properties of our data are relevant and other properties are not. And the network should learn to distinguish between things that are relevant and that are not relevant. For example, if you try to understand what color, what type of fruit you're depicting in an image, the color is definitely very important and can help you to distinguish, say, an apple from a lemon. but the brightness of the image or the contrast should not affect it. The shape, yeah. The rotation of the object, no. So there are some properties where we can try to kind of normalize our input to make it easier for our network to learn, okay, those things are always the same, like they all have the same kind of brightness distribution, so I can basically safely ignore that. Otherwise, we might run into the situation with the ruler. If you remember the example from the very first few lectures, where the network learned to take a look at the ruler instead of taking a look at the melanoma to classify whether it's good or bad. So another example would be the audio sampling rate if you work in the audio domain. Think about it. If you sample your input with completely different rates and then just feed those to the network, it might look as if someone was talking much faster or slower, which is not at all related to the content that is being recorded in that audio. And finally, if you rotate a page with text, it shouldn't definitely should not change the content that is written on that page. We can try to normalize our input data to kind of even those slight variations out and try to come up with a very homogeneous training set. So here you see an example of people who are not normalized, and once we normalize our input for the brightness and the contrast, they all look, at least to me, much more homogeneous. Image normalization, let's talk about this, how you can actually implement this, what I've just showed you. Brightness normalization can be done by mean subtraction, so you just compute the mean brightness of all your samples and then subtract it. Contrast normalization by a division of the standard deviation, or you can do histogram equalization to take a look at the histogram and try to even that out. And for color images, what you're typically doing is you're doing it per channel. So here are some examples of your original, and then you apply some sort of normalization or histogram equalization, and you can see that the images now are much more looking like the others. Preprocessing can even be essential to make your network work at all. So if you present this page of handwritten text to a machine and ask it, so please tell me what's written on that page. I mean, even for humans, this is very hard, but a machine will probably just shrug and say, I have no idea, how should I proceed here? So applying the right preprocessing step makes this problem go from unsolvable with neural networks to very hard and challenging, which is already a big step forward. One way how you can actually do this for text, it's a very common procedure that you try to find the baselines of your written text. Try to find the line where text is being written upon, and this baseline detection is now a preprocessing step that you can use, and that transforms the problem in a kind of one-dimensional problem where you just follow along the baseline and then you can feed that part of the input into your neural network. Of course, the image is still a two-dimensional image snippet, but by one-dimensional I mean that you can now only read from left to right or right to left, so you just have to follow that baseline instead of trying to navigate where in the image you should read your next letter. Preprocessing is definitely domain specific, so if you're working on text, you might need different preprocessing than when you're working on music scores. What I've been doing on music scores was also domain specific, so kind of the baseline, if you will, for music scores are those 5 lines, and those are called stuff, and you try to extract one stuff at a time to break down the problem. And so what you would do is kind of try to find those stuffs and then process them individually. Coming from making data look more similar, we can also now try to make data look more different. The idea is that ideally we want to train on as much data as we possibly can, with a large set of variations that capture the underlying distribution fully. And as we add more data to our data training set, we usually increase our performance because the data now reflects our problem much better. We can kind of approximate the underlying distribution to a higher degree. Unfortunately, getting more data is not always possible, or it might actually involve human suffering. If you think about data sets that contain pictures of people suffering from certain diseases or rare diseases, it can be very difficult to get more samples of them. So ideally we want to kind of get around and work with whatever data we have, with as much data as we can possibly gather, but sometimes we have to do with a little bit less. Data augmentation therefore comes handy where we try to create meaningful fake data. What data augmentation does is that we're trying to use transformations to increase our training set size, which is exactly what we want, while at the same time staying within our distribution and not changing the semantic of our input data, obviously. The effects of performing data augmentation can now be observed as the following. We can increase the diversity in our dataset. If you think of an image that is only being recorded at a perfect angle and then you start rotating it, our network will learn how to cope with images that are slightly rotated because it has seen them now during training. If all images are perfectly aligned and then at test time when you're performing inference, you show it a slanted image, it will not work that well because it's never seen that in the input. Which brings me exactly to the second point. This slight variations, we're now gaining some form of robustness against those slight variations by applying the right augmentation methods. It improves generalizability to samples that we haven't seen before, and on the downside, it also increases our computational costs because we now have to pre-process our images somehow to look a bit differently each time we take that image and train on it. This is mostly done online, so we perform our data augmentation as we are performing our training, and we're not even storing those images. For example, let's go back to the image domain. When you're performing an image augmentation like a rotation, we can take a sample, load it from disk, or if it's already in memory, even better, rotate it and then feed it through our network for the training step. And the next time we're loading that image, we can apply a different rotation. And if you would store all the images with all possible transformations and augmentations, this would not fit anywhere on your disk. That's why you typically do this online and you're not storing those images or those objects, but just performing them online. Now, if you perform this online, it has the drawback that you're not only using your GPU for the training, but you're also quite heavy on your CPU because most of the time those transformations are being performed on the CPU. So as a practical tip, if you perform heavy data augmentation, make sure that you also have a powerful CPU and enough RAM on your computer to enable this and not have the data augmentation be the bottleneck of your training procedure. Finally, coming back to this semantic of the data, be careful with whatever kind of transformation you apply. Some transformations do not change the semantic, others do. If you flip an image horizontally, it might be okay for a cat, But in other terms, when you are working with text, a B then could look like a D. Or if you perform vertical mirroring, well, you would get something that now says something completely different. So make sure that whatever transformations you apply as data augmentation does not alter the semantics in your particular data set. The most common transformations for images are rotation, random scaling, where we kind of try to zoom in or zoom out of an image, random cropping, where we just cut off some parts, and of course mirroring. At least for cats, this works fine because a cat that you mirror horizontally is still a cat. You can even apply some of the more advanced augmentation techniques for images, which could be sharing, some kind of non-linear stuff or some cutouts where you just drop certain parts of your input image, masking, similar idea, and even some really fancy three-dimensional transformations that make your image look as if you kind of had a physical printout of that photo, you crumbled it together and then unfolded it again, which gives you something that looks like this. I think this is a fantastic idea. There are some great tools. I've linked one tool here in our references that you can go and check out to see if any of those transformations might be useful for you. Another example for data augmentation that should not alter the semantics is so-called adversarial training. Let's start with an image. You're on a plane and you're in the cockpit. And the cockpit has hundreds of knobs and turns that you can change. So changing one knob slightly shouldn't do much. However, if you change all the knobs, even just for a tiny little bit, at the same time, the effects can be quite dramatically. That's the idea of adversarial training, that even neural networks that have human-level performance or nearly like performance that is exceptionally well, all have a nearly 100% error rate on carefully crafted adversarial examples. So those are malicious examples that try to break your network. An adversarial example is more formally defined as x prime that is near x, so the inputs are very similar, but y prime is quite different from y, so the output is completely different. And the reason why this is happening is because most neural networks are built primarily out of linear building blocks. And those linear building blocks are very sensitive to simultaneous changes in numerous inputs. Changing just one neuron usually doesn't have such a big impact, but if you change all neurons even just a tiny little bit, these linear building blocks are very sensitive and can have severe effects on the output. If we perform adversarial training, we would enforce locally constant behavior, and how we do this is basically by just adding a little bit of random noise to our input. We really have to be careful with our neural networks if you put them out in the wild in the future, because like we are the ones who might be building the next object detector or something that powers self-driving cars. However, if it's so easy to fool these networks, we should really be careful on what we rely on and how we can maybe try to make those networks robust against these adversarial examples. Self-driving cars is just one example, but think about, say, fraud detection. By having a neural network that tries to detect fraud and kind of breaking into this and understanding what you need to alter to break the network and to say, well, there is a positive, you can carefully craft an attack against your neural network. And this idea of trying to attack a neural network by adding a little bit of noise to break it has become its own research field, because the more systems that we actually deploy and use and rely upon, the more important it is to protect ourselves against such attacks. In some extreme cases, the authors of this paper have shown that even just changing one single pixel can be enough to alter the predictions of the neural network. They employed a special method to find out how to change the input, like which pixels are having the biggest effect. And here in those images you can see that they highlighted the single pixel that they actually changed with a red circle. But I think it's very impressive that there is a method that can change your input so little, like just a single pixel, and still have an effect on your network's output. I really love that example. In this paper, they show an adversarial attack on modern object detectors with convolutional neural networks. And what they did was they carefully crafted an image that does not produce any output in our object detectors. And if you print that pattern on a hoodie and you wear this hoodie, you can actually show that you become invisible to these object detectors. So this is kind of a modern day invisibility cloak if you do not want to be tracked by one of those modern object detectors that we've talked about in the past. When we now leave the domain of images, we can go into the audio domain, and also here there are a bunch of data augmentations that you can apply to your data. For example, you can inject noise, you can shift your samples in time, you can change the pitch to make it sound a little bit higher or lower, or you can just change the tempo of what you've recorded. And ideally, if I say a sentence slowly, or if I say it very fast, it shouldn't make a difference in whether you understand what I'm saying or not. There is a great library that enables you to do many of these augmentations. It's called librosa. Go check it out if you're working with audio. Let's take a quick look at some examples of these augmentations, how they sound like. So that's the original. Let's shift the end to the beginning. So it cut some part of the end and put it to the beginning, or it was maybe a different part of something that came before. We can add some noise. Or we could stretch it in time. Maybe you didn't hear it that well, let's play it again. So you could hear it was much slower than the first few ones. Or at least a bit slower than the first few ones. Furthermore, you can perform many of these data augmentation operations for audio actually in the image domain. The idea is that for audio processing, many modern approaches rely on spectrograms, where the audio waveform is being transformed into an actual image, and when you transform it into an image, you all of a sudden have access to all of the operations that work well on images for your audio domain. You can perform time warping, where you kind of randomly increase the speed or decrease the speed in your input. You can perform time masking, which you can see over here, where we just cut out a small part of our input, like these two parts. Or we can do frequency masking, where we remove an entire frequency spectrum from our input. So one sample just does not have any information, say the frequency range between 10 and 12 kilohertz. And that would be frequency masking. If we go to the text domain, you can also apply some meaningful data augmentation techniques here, like synonym replacement, where you replace one word with another word that has the same meaning. a synonym. You can perform random insertions where you just attach another random word somewhere in your input, and the network should still kind of be able to make some sense out of it. You can swap words randomly, or you can delete words randomly. Of course, you might break the syntax because as said, superior human out on the road of life. Well, actually that one does make sense, but maybe with random swap you can actually break your syntax. As said, superior human comedy played out on roads back of life. Yeah, this definitely does not adhere to a standard English syntax, so that input sample would be broken. However, we randomly perform these operations and the network should see the correct order also often enough. You can even make use of some kind of errors that are being introduced when you translate sentences into another language. The idea would be that you perform back translation. You take an input, you translate it to another language and translate it back. And what you will get back is a slight variation of your input, because words can have many meanings and it's not necessarily that you end up with the same input that you fed into the original translation. So this is kind of a clever mechanism how you can increase your text corpus to have more samples by just translating it and then translating it back. If your translation works fine, it should keep most of the syntax and semantic intact, and your corpus should still have the same meaning. Data augmentation is also domain specific in the same way that preprocessing is domain specific. If you want to perform data augmentation on images of music scores, you can create new music. You just randomly generate a sequence of notes and then you render it and you get a new piece of music. It doesn't have to sound good, it just has to look like real scores. If you can achieve that, you can generate as many samples as you want as part of your data augmentation. You just create music scores on the fly and then you can train your network to perform operations on these. Just remember, when you're relying on synthetic data, the process by which you generate those samples will determine your underlying distribution. Therefore, you will always need some real data in your dataset as well, because the variation that you will get from those synthetic samples might not cover the entire true distribution that you could encounter. So just keep this in mind. Coming to the next topic, where you now bind our shoelaces, regularization. The central problem in machine learning is how to make an algorithm perform well on previously unseen data. We don't necessarily have the network perform exceptionally well on the training data. We want it to work good on the test set and when we perform inference on new unseen data. Regularization is one technique that can help us achieve this more efficiently. Regularization is a set of strategies that are designed to reduce the test error, potentially at the risk of ending up with a higher training error. What we're doing is we're limiting the model capacity to avoid overfitting on the training set. Data augmentation, as we've just seen before, is one mechanism how you can perform some sort of regularization, and it's actually a really efficient strategy. But there are also a couple of other strategies that we're going to take a look at. Some add restrictions to our parameter values, some add maybe an additional objective function. We've already talked about these auxiliary functions, for example, in reinforcement learning. So we can encode some sort of prior knowledge that we have about the underlying problem. And of course, we can use ensembles, where we have multiple networks that work together. Model ensembles are, as I just said, multiple networks that are trained independently, but then are being used jointly. The idea is that you have the same model, but you initialize it differently. Every model is initialized with random variables and then they're trained on the same data set. If you start from a different point with a different initialization, the idea is that you end up at a different optimum. So your network might make certain mistakes, but another network that was trained on the same data but started somewhere differently might make a different mistake and not make the mistake that the first network made. So if you run your sample through multiple networks and then kind of take a voting process to see which one should be the desired output, then you're kind of averaging your predictions and you're trying to avoid errors that only one of those networks produced. You're kind of a quorum now that votes for which output to actually predict. Weight decay is also a very popular regularization mechanism, and it's adding an additional objective function by adding a parameter norm penalty. What we're doing is that our objective, when we describe our parameters of our when we describe our learning, that instead of just computing the gradient descent, we also add a penalty term for how big our weights in our neural network are. We typically only do this for the kernel, for the multiplicative weights, and not for the bias term. And typically we also use the L2 parameter norm penalty that we can compute just by having a transposed weight multiplication with the weights. If we use weight decay, our gradient update step now becomes slightly different. As you can see here, we have the weights and then we subtract our gradient that we compute. So what happens here is that the coefficients that we're computing, our weights, our new weights, will shrink for every update step that we perform. That's why it's called weight decay. Our weights become less and less. And the rate by how fast they become zero, ultimately, is determined by our weight decay parameter alpha. And that is typically a very small number between 0.0001 or 0.001. Weight decay in practice, for example with Keras, is that you basically just specify in your layer kernel regularizer and you say, well, take the L2 norm, that's basically weight decay. For PyTorch, there is a specific parameter called weight decay, and you just specify that one parameter that says this alpha value of how fast your weights decay towards zero. One of the most important regularization mechanisms that I highly recommend every one of you to use is early stopping. How it works is that you monitor your training on the validation set. You should do this anyway by just saying, okay, after each epoch, compute some statistics, some loss, maybe some precision or any meaningful value on your validation set. And you save the models during training, and then you perform after each epoch, you save the model and then you continue training the next epoch. So when you are at the end of your training, instead of returning to the last model that you trained, the last training step of the last epoch, you actually return to the epoch that had the lowest loss on, or the best performance on your validation set. It could be that that moment was already a long time ago, but what that means is that your network continued to training and overfit your training set. So monitor your validation set, and if the performance on your validation set does no longer improve for a certain time, you can stop training altogether. It's highly effective simple to implement, and basically almost a free lunch. So take this and put it into your neural networks whenever you train something with machine learning and neural networks. The effect of this early stopping is that we control the effective capacity by limiting the number of steps the optimizer can take. Weight decay does a similar thing. If our weights decay towards zero, we are limited by that amount of steps that we can take in our network. If we take too many steps with a too high weight decay, all of our weights will be just zero. The good thing about early stopping, when you compare it to weight decay, is that it automatically determines the correct amount of regularization. So we don't have to worry whether we use the right alpha value for this weight decay, because you just monitor on your validation set and stop when you don't see any further improvement. Cutout is something that I think I mentioned before. So you can take, for example, for images, certain parts of your input and just remove them, set them to zero, and kind of make the network forced to be able to understand images, even though some parts of the images are hidden. Dropout is a very common regularization strategy that I think lost a bit of popularity recently, or actually over in the last few years. However, you can still find it in quite a few networks. What it does is that you have your network, and with a certain probability p, you set the neuron's output to zero. Regardless of what you feed into, that neuron just produces no output. It's independent for each sample or for each mini batch what neurons are disabled for that pass. So you're discarding neurons during training, and when you perform inference on your final set, or when you do testing on your test set, all neurons are active. So what is the effect of this? You force the network to not rely on individual neurons too much, because they could just drop out and then they wouldn't produce any output. So the neural network has to also learn to rely on different paths and different features of your input, because one particular feature could just become zero at one point and the network still has to produce a good output. The effect of applying dropout to your neural network is pretty similar to an ensemble. So your subset of neurons that you have in your network works as if you had trained another network, and in the end you deactivate dropout for inference and for testing. So all of the networks that you trained in parallel are now working and operating at the same time. Batch normalization is a regularization strategy that is a bit controversial, but very popular, and you can see it in almost every neural network in one point, especially whenever we talk about convolutional neural networks. In general, it is hard to train a large neural network because of so-called internal covariate shift. What is this internal covariate shift? We define this internal covariate shift as the change in the distribution of the network activations due to the change in network parameters during training. So what happens is that in one layer we perform a certain operation and that output follows now a certain distribution. If we now train on a different sample, that distribution that is being produced is different. So even if your input data is normalized, we have zero mean and unitary variance, the distribution of these intermediate layers is constantly changing back and forth. And the gradient tells us how to update each individual parameter. But the underlying assumption is that all of the other layers that we computed our gradient for does not change, because we're just computing the partial derivatives with respect to just one parameter. So this constant shift in our network can become a serious issue. Batch normalization initially came across this problem and thought, well, we can then normalize our layers. So what you do is that you think, okay, let's try to combat this internal covariate shift by calculating the mean and the variance of the input. And then we normalize our layer inputs to calculate with some calculated statistics that we compute during training and fix during inference, and then scale and shift our data set to obtain the output. And how we should scale and shift our data is learned during training. That's batch normalization. Interestingly, batch normalization has seen quite some controversy because people thought that it was combating this internal covariate shift. So the assumption was, well, we know that internal covariate shift is bad. We think that batch normalization is reducing that, so we know that empirically, when we train and we use batch normalization, that the performance increases. So, well, batch normalization therefore works due to reducing this internal covariate shift. However, there were some researchers that had doubts about this hypothesis, and they did what every good researcher does. They went and took a look at whether this is true or not, this hypothesis. So they questioned this and they showed that it does not, in fact, reduce this internal covariate shift. In some cases, they could even show that it increased those internal covariate shift. Then the question is, what does batch normalization do? And they found out that instead of reducing this internal covariate shift, it smoothens out the gradient. And smoothing out the gradient has a similar effect of improving our performance. So if that is our gradient, we're trying to get the ball down to the lowest point. We have these bumps and then we might have to take steps in the wrong direction, or we get back up because we bounce up. Instead, we have a much smoother gradient and it becomes much easier for the network to learn how to optimize on our training dataset. So the good news is batch normalization works exceptionally well in practice, and it's definitely advisable to use it, even if some researchers say you should definitely not use it, should use something else instead. Which is the bad news, that it's not fully understood why it's working so well. I mean, we know that it smoothens out the gradient, but there's still some doubt on how exactly batch normalization works. Batch normalization in practice can replace some other regularization techniques like dropout. And the question then is, where should I put this batch normalization? And there is no clear answer to this. People have put it before the activation, after the activation, somewhere in between one of those modules. And you can see that there was not a clear winner of saying you should always put it behind the activation or before the convolutional layer or after the convolutional layer. So there are some I would say, papers that explored this, but I haven't come across any paper so far that was able to say you should always put the batch normalization at this point. Meaning that you basically have to experiment and see how it changes your network, and maybe putting it right after the convolutional layer is much better than putting it somewhere else. One thing I would like to point out here is that batch normalization isn't the only way to stabilize the gradient. Layer normalization is a popular alternative to batch normalization. And how it works is that it directly estimates the normalization statistics that we've seen before from the summed inputs to the neurons within a hidden layer. What that means is, let me visualize this for you. If we have a batch with 3 samples here, and those are our input features, x1 through x4, then what batch normalization would do is it would calculate the statistics, the mean and the variance for each feature. So here across the features x1, 2, 3, and 4. But as you can imagine, this is now sensitive to the size of our batches. So if you have a small input batch size, the output statistics that we compute here are very sensitive. And you also have to imagine that for training and for inference, we need a slightly different set of operations to perform batch normalization. Layer normalization, on the other side, would compute those statistical values for normalization for each sample. So not across feature, but for an entire layer for each sample here. And there are other normalization methods too, for example, instance normalization or group normalization. One activation function that can actually also function as a regularization mechanism is the so-called scaled exponential linear unit, SELU. And it has been described in a paper called Self-Normalizing Neural Networks. And the hypothesis is that when you use that kind of activation function, your neural network automatically normalizes its output to be stable. And if this network output from each layer is stable and does not have this internal covariance shift, we don't need batch normalization. And this is how you can compute this. It's quite a simple to compute activation function, and I think it would be interesting to also try this out in a couple of neural networks to see whether they actually perform better. Stochastic weight averaging is a simple yet very effective way to improve the performance of your optimizer by averaging the weights. What does it mean here to average the weights? What we do here is we take two basic ingredients to improve the performance of our neural network. And the underlying idea is that usually we reduce the learning rate of our optimizer towards like a very low value to converge towards a single solution. That solution is ideally the globally optimal solution. But if you visualize the gradient surface, the solution, so what we end up with typically is kind of a large flat area. And the solutions that our optimizers do is, because of the volume of this thing, typically at the edge of this flat surface. So how about we explore this flat surface a little bit and try to find the center of it? So what stochastic weight averaging does is, it basically says, let's modify the learning rate and keep exploring good solutions. So you can see it in the left bottom image here is that initially we start with a high learning rate, and then we perform our usual decrease in learning rate for, say, 75% of the training. And for the remaining 25% of the training, what we do is we keep actually a learning rate that is not too low. So we keep a moderate learning rate, and we keep track of the weights that we compute here after a couple of steps. This allows the network to, keep exploring good solutions. And once we're done with the last 25% of our training, we take those snapshots of those weights and we average them and compute the average values. And as you can see here, also for batch normalization, this would require some special handling, but I'm not gonna get into those details. What you can see on the right side, however, is very interesting. You see the blue curve, the test error, and the green curve, the training error, or the training loss, more precisely here. And what's interesting is the discrepancy between the curves and the solutions that they provide. So from a pure optimization performance, stochastic gradient descent, the green thing here, would give us the lowest value of the training loss. But when you compare that to the test error that we obtain, you see that it's not the optimal solution. And they've shown that for many cases and in many scenarios, this stochastic weight averaging that you perform like for the last 25%, you memorize the weights and then you average them out, allows you to find the center of this large flat surface that generalizes better and therefore obtains a lower test error. And stochastic weight averaging works in tandem with any other optimizer because you just perform stochastic gradient descent as you would do it before, but you just keep track of those weights and average them in the end. So it's a very simple yet effective way how you can improve potentially the performance of your neural network even further. Coming to the last part of our lecture today is visualizing our training and visualizing our network. One thing I can absolutely recommend is the Tensorboard, which gives great insights into your network, how it performs, and is an easy to use interface for exploring your data, exploring your training progress, and monitoring your progress as you train your neural network. It's available for all sorts of platforms and frameworks. It was initially created for TensorFlow, but it can be used with many other deep learning frameworks as well. I'm now in Google Colab again, and this is the sample notebook that TensorFlow provides to play around with the Tensorboard. And the interesting thing is that the Tensorboard obviously works standalone, but you can even embed it into a Google Colab notebook. And for demonstrating how this works is that we train a simple network here to, I guess, perform image classification. It's the standard thing that they're trying to do. So when we're starting, so we're training here for a bunch of epochs, say for 5 epochs, and then we can open the Tensorboard when we just point it to our logs. And what we get is a beautiful interface that is white. No, here it is. And we get a beautiful interface that we can use to explore some of our data. So we trained it for 5 epochs. They were enumerated from 0 to 4 here. And you can see the accuracy for each epoch on your training set and our validation set as we move along here. So that's really interesting, and you see, okay, the network performed much better in the 4th epoch, which was to expect. And you can use also that if you have to manually perform early stopping, but just looking at those graphs and then stopping. I think they're also demonstrating this here, that you can start the Tensorboard and then run the training, and it will dynamically update over time. So you can have kind of a separate process that performs this Tensorboard, that runs the Tensorboard, and your training process. And they run in parallel, and it automatically loads data from the disk where the logs are being written to. Some of the interesting aspects of this Tensorboard is the wide variety of features that it offers. One would be, of course, showing some scalars. If we have an image processing problem, we can also, and images are being written to our Tensorboard, we can also take a look at those images. For that example here, no images are being written, but we can explore the graph. So that is our neural network. We can also explore some of the distributions of our individual layers. And maybe we can see that they look kind of okay-ish here. They're centered around 0. But it could be that some layers completely drift off or do some crazy stuff. You could maybe see it here. And some of the interesting diagrams here that I'm not fully aware of how to interpret them. But basically, you're seeing some values here over time, like for each epoch here, how the distribution looked like, I guess. So feel free to play around with Tensorboard and find out what else it has to offer. It's a great tool, I think, and I'm using it for basically whenever I train neural network, I'm automatically writing information to in the Tensorboard format to disk, and then just run Tensorboard to quickly be able to play around with this and explore my data. One very nice tool that I've come across to visualize your neural network architecture is called Netron, and I highly recommend that you check it out. It supports a wide range of tools, and you can drag in your configuration or your model and then visualize the architecture with all of its parameters, etc. here in a nice visual way. Another very powerful method of exploring your data and exploring your network is by so-called class activation maps. The idea is that we map the weights of our output layer back to our feature maps. So what we do is we have an image and we feed it through our network, and that obviously results in certain features that are being computed before the final state that performs an operation. So we take those features, we multiply them with the weights of our last layer, and that gives us an activation map which says which features were related to which part of our last layer, which still has the spatial information for images, for example. And what you can see here is one of these, I think, really fantastic visualizations of these class activation maps to be able to say, okay, the network learned to classify whether this person has a disease or not by looking at this area. So it can kind of say, doctor, the network predicted this to be symptomatic because it had something over here. And then the doctor can use that information to look at that particular part of the input and be more efficient in trying to diagnose patients. As I said before, what we're doing is we're computing the features in our output, and then we're multiplying them with the previous layers. We can do it with the last layer. We can potentially also multiply the features that we have with earlier layers. Thinking back of class activation maps in the context of global average pooling, if you think back and you remember what global average pooling was, it was the idea that we kind of shape our output in such a way that we have one layer per output class if we have some sort of image classification problem. And then we just map that class to our output to not kind of reshape our input image, but just perform global average pooling. Now, if we use global average pooling, the effect would be that the last layer is the feature map for individual types of our output, for individual classes. So if we multiply this, we can see how much it activated for certain parts, for certain classes in our output, and maybe even learn how close certain classes are to each other. Let's take a look at some code for these class activation maps. What we have here is our beloved MNIST dataset where we perform image classification, and then what we're trying to achieve is that we're going back to those class activation maps. So we take our usual dataset, we pre-process it to load it into memory. So if we just show a random image, we can see, okay, that's an 8. Of course, those are black and white images, but if you visualize it in terms of grayscales, you can also show it as a sort of heat map. And then we have a fairly simple neural network with a few convolutional layers and global average pooling at the end, which has 10 outputs. So in that case, it's not the global average pooling. We still have a, so it has the 128 things, but then a dense layer afterwards. So we reduce it by using global average pooling, which is another way of how you can do it. And then we just train our model. And after a couple of steps, we get 99% accuracy. That's a nice visualization of the model. And what happens now is that we try to evaluate this. So we run our dataset again, or some samples from our test set. And what we use is we first get the weights of the last layer before the end. So those features, I guess now from the global average pooling, if we have, say, 128. Anyway, what we take here are the weights from those last layers from the global average pooling. And when we're running it through our model, we're producing multiple outputs. One would be the standard classification, and the other thing here is that we actually want in our outputs now for this the information from the layers before, like near the end. So the last few layers, so -3, 1, 2, 3 would be this convolutional layer, I guess, and -1 would be this dense layer, if I'm not mistaken. So we predict a model on our test set, and then what we do is exactly what I said before. We're multiplying here, we're doing the dot product of the features that we extracted. So those are like the features from one image that are zoomed to the size that we want to have, with the weights from those last layers that we have here. So that, I guess it's the dense layer here at the end. And what we get is a heat map that we can now overlay over our input to get these beautiful images, which state, okay, the neural network mostly relied on the information here to say whether this is a 2 or not, which I guess makes sense because most other numbers look quite differently here. So if you have 1, it looks differently here, 3 goes in the other direction, 4, 5. So all of the other digits, if I'm not mistaken, have a different shape down here. And even if you have a 4, it would even make more sense to look at this part, because that particular curve here would have another line here for a 4. So for 1, it makes sense to take a look at everything in the surrounding. If you just have a straight 1, well, there's probably nothing, and so on and so forth. So you can see the network trying to make some sense out of these inputs. If it's directly interpretable or not, I'll leave it up to you, but I think it can be at least helpful for certain problems if we're able to see which parts of the network were active and the network was looking at. It's kind of the attention mechanism, but for us humans. I've attached one more notebook from the slides here where we're not using max pooling, but I leave that for you to explore and see the effects of what happens if you have your network without max pooling. There is an idea of visualizing not just the activation maps, but also the training process in itself. And the training process in itself is the gradient. So we can try to understand how our network is kind of getting to the bottom of the valley. The same idea that I try to give you with this gradient descent. And there is a gradient visualization toolbox that you can try out and play around with. And there you can see how the gradient looked like and how the network tried to go down to the valley here, and maybe find some interesting ideas. I just have to warn you, visualizing the gradient is feasible for small problems. However, when you have a very large neural network, it can be computationally expensive to compute that visualization. Summing up today's lecture, I hope you got some ideas for how you can fine-tune and improve your networks by using data normalization, as it is a very important preprocessing step, because many of our parts of our neural network, like initialization algorithms, rely on the assumption of having normalized input and having normalized weights during training, like batch normalization, silo can be mechanisms to enforce this. Preprocessing can make some problems go from the domain of unsolvable to at least somehow solvable, so they become tractable, and as always, you need domain-specific knowledge for those preprocessing steps to be able to develop them and kind of have this initial idea of how you want to preprocess your data to make it work. Large networks need proper regularization. I told you before, the best performing neural networks are those that have a huge capacity but are well regularized. So what we can do is we can employ several mechanisms at the same time, like data augmentation, where we create meaningful data. We can employ weight decay. Early stopping is something where we stop when we see no more improvements on our validation set, which is both beneficial for the output performance, for the overall performance, as well as we're saving time. So I would definitely recommend this one. Dropout, where we can intrinsically train model ensembles, or batch normalization. And finally, when you visualize your gradient or your activation maps, it can help you to get a somewhat understanding of what your network is internally doing and where it's looking. We explore this a bit more in the final lecture of this course, where we talk about explainability and explainable AI, but for now, I'll leave you with that. I wish you a wonderful week, and I'll see you next week.